Thank you.
So now for something very different, as Monty Python would say. This is an endeavor that my brother David first did, and I see that he's already joined us, which is nice. And another David Vulach, is coming in from Boston, who's worked a little bit on this when he was a high school student. I first saw this when I was a high school student. And so this is a mathematical excursion it's something my brother came up with. This is my brother David. You've already met my brother. Well, you might have last week seen my brother Barry, and my son Asher gave a keeping current thing. I'm trying to keep this in the family when I run out of things to when I run out of people to talk about things. So I'm going to share a screen here and show you something which I consider pretty neat. Prime probabilities. And what I'm going to do is show you this with a blackboard. And so when is a number prime? That's the question. So here, a number is prime if it is not divisible. By what? Well, divisible by anything? No, you have to worry if it's divisible by integers. So a number, let's give the number a name. We'll call it n. And we'll look at divisible by integers. You only have to worry about divisibility by integers, I, such that 2 is less than or equal to I is less than or equal to the square root of n. You only have to check up to the square root of n because, for example, the number 6, it's divisible by 2. So I don't have to check for divisibility by 3. I only have to check up to the square root of n. Right, that's the first assumption. And it's not a difficult assumption to believe. In fact, that's a definition. But the next one is going to be a little bit harder to believe, and it's an assumption. What is the probability that I divides n? Well, either it does or it doesn't. By divides, I mean divides exactly. However, if you want to call it a probability, I'm going to say it's 1 over I. So, for example, 1/3 of all integers are divisible by 3. 1/5 of all integers are divisible by 5. And so what's the probability that 37 is divisible by 5? Well, we know that it isn't, but we'll say it's 1/5. And that's an assumption that I'm going to make in order to have the rest of this work. And the third and last assumption is if I and j are prime, then divisibility by I and by j are independent. And when you talk about things being independent in the world of probabilities, let's see if I can spell that right. Independent. In the world of probabilities, that means that I can multiply probabilities, which I'm going to be doing. So now I'm going to start looking at some numbers and ask if they're prime. Consider 2. Is it prime? I only have to check for numbers that are, let's get the pen up here. Yeah, numbers that are from 2 up to the square root of 2. Well, there aren't any numbers that are between 2 and the square root of 2. No integers, because the square root of 2 is about 1.4. So I don't have to worry about that. 2 must be prime. Because there are no potential divisors. So it's vacuously prime. Consider 3. Well, the square root of 3 is about 1.7. It's also going to be vacuously prime, must be prime. So we know that 2 and 3 are probability 1 primes. And I'll be using P of n as just a notation. P of n is the probability that n is prime. And again, this is kind of a strange thing to talk about because any given number either is or isn't prime. Nonetheless, we're going to pretend that we can talk about their probabilities just as we can talk up here about this very strange business about a probability of divisibility. Right. So the next question, the next thing to consider is 4. And is 4 prime? Well, all I've got to do to answer that question is to consider all its possible divisors. The only possible divisor is 2. There aren't any other possible divisors because the square root of 4 is 2. The only integer between 2 and 2 is 2. Well, does 2 divide 4? Well, you're not allowed to say, of course it does. You must say the probability that 2 divides 4 is 1/2, based on this rule up here. And therefore, the probability, oops, wrong pen, sorry. The probability that 4 is prime has got to be equal to 1 minus the probability that 2 is prime. I'm sorry, I'm going ahead of myself here. 2 is prime. So what I just said is reasonable, but not what I want to say now. It's 1 minus the half that is the divisibility. So this, oops, sorry about that. This particular, if I touch this in the wrong place, things go wrong. So this is the probability that 2 is prime. And together, that's therefore the probability that you are not divisible. Again, I got ahead of myself. Hold on a sec. I want to say these things in the right order. This 1/2 is just divisibility by 2. So it's 1 minus the divisibility by 2, and probability of 4 being prime is therefore 1/2. And I can use exactly the same argument for 5, because 5 has got exactly the same possible divisors. Namely, I only have to check by 2, because the square root of 5 is 2 and a little bit. It's not up to 3. So the probability that 5 is prime is also 1/2. Likewise, up to the probability that 8 is prime is 1/2. Once I get to 9, I've got another divisor. But up to now, it's all 1/2. And so I would expect that about half of those numbers are prime. Now, how many numbers are there? There are 5 numbers, 4, 5, 6, 7, 8. Half of them should be prime. Well, in fact, half of them are prime. Well, 2 of them are prime. So 2.5 numbers are expected to be prime. 2 of them actually are prime, 5 and 7. So this gives us some hope. Now we're going to consider 9. Well, it's 1 minus the divisibility by 2. That's the probability that it's not divisible by 2. And I'm going to invoke my third assumption here, that divisibilities are independent. And therefore, it has to be both not divisible by 2 and not divisible by 3 as independent things. Well, you do the arithmetic. That's 1/2 times 2/3 is 1/3. So you'd expect about 1/3 of the numbers between 9 and the next square, which is 15, are going to be prime. There are 7 such numbers, and so we expect that 7/3 of them are prime. That's 2.3. And in fact, 2 of them are prime, 11 and 13. So again, it's working pretty well. So I'm just to say that equals the probability that 10 is a prime equals all the way to the probability that 15 is prime. Something new happens now at 16. You might think that you should just do this multiplication. However, we have to adjust this a bit because we don't know if 4 is prime. In fact, it isn't. And the fact that it might not be prime means we maybe shouldn't be doing that. But we do know its probability of being prime. And the probability that 4 is prime happens to be 1/2. And so what I'll do is I'll modify this slightly. Instead of 1/4, it's the probability that 4 is prime divided by 4. Which means it's not going to contribute so much to this product because it might not be prime. And I certainly don't want to consider division by a non-prime because I've already covered it in division by its prime factorization. All right, and so this happens to equal, I actually have computed this, and it comes out to 0.29, approximately 0.29. And so we'd expect that of the 9 numbers between 16 and 24 inclusive, that about 2.6 of them should be prime. And in fact, 3 of them are, 17, 19, and 23. So it's working pretty well. General formula, we can write down now. The general formula says that the probability that n is prime is the result of a product. And I'll consider all possible divisors and again, I must be integer, of the term 1 minus p of I divided by I. That's the general formula. And if you know the probability that a particular number is prime, or all the numbers within some range are prime, then you can compute an interesting value. So we're interested in that interesting value, interested in total number of primes less than or equal to some number n. Now, unfortunately, mathematicians have a name for that, which is pi. And I've already used pi to mean product here, but that's not going to stop me. This is called, excuse me, I'll erase back. Okay, this is called pi of n, and I'll make it an italic pi, all right? Pi of n. And so we can compute that by just taking these probabilities, like probability of 16, which is going to be the same as the probability for 17, 18, and so on, and multiply it by the number of elements in the range that have the same probability. There are 9 such elements. And so I can add that to the probability that 9 is prime times how many elements have that same probability. There's 7 of them. And the same thing for probability that 4 is prime, and the same thing for probability that 2 is prime. And I can keep a running total. And that can be done by the computer. So by computation, we can estimate both p of n and the number of primes less than n by just starting with a small n and moving higher and higher. Actually, we jump up by squares. So we first look at p of 2 squared. Well, p of 1 squared is not a prime. It reminds me of the old joke. How do you know that all odd numbers are prime? And the computer scientist says, oh, a mathematician friend of mine once told me that, so it must be true. Well, this is computer science making, doing mathematics with some very strange assumptions, but okay. We can estimate this by going up by squares. And we would look at prime P of 2, P of 2 squared, P of 3 squared, P of 4 squared, and so on. And we can then compare against actual values. Well, how do you compare against the truth? You find tables, and there are tables. There exist. I'll use a mathematical symbol. There are tables of primes. And you can get such tables in various forms. Nowadays, you can get it on the computer. When I first did that, this was well before computers were doing that or before the internet. And so I referred to the Handbook of Mathematical Functions by Abramovitz and Stegan, a great volume that I recommend to everyone. And that actually has a table of primes. This is good until you run out of room on the table. And you can very quickly compute values of P of n and pi of n, which exceed that table. And so what do you do next? You rely upon some deeper mathematics that I've never tried to look at proofs of even. And that is, it is known. This is my reliance on mathematics. I'm the computer scientist saying a mathematician of mine, a mathematician friend once told me this, that pi of n is approximated by the logarithmic integral of n. And that same Handbook of Mathematical Functions by Abramovitz and Stegan has got a table for the logarithmic integral, and you can interpolate into it. And it goes far enough. So that's what I use when I can't actually compare against tables of primes. So what does the computation actually look like? The computation says, looking at the next square, because you might as well jump up by squares, you can use we can use the previous value of this, and we just have one more term to add into it. So it's a recursive thing. We start with the P of n minus 1 squared, and then we put in the new term. And the new term is 1 minus P of n over n. Because the new term is the next, is the last integer that is less than or equal to the square root of this number. And that number is, of course, n itself. And so that last term is this one that I've shown you here. So you can have a running value of this, and you just multiply that, which means you've got to store some values. Because when you're worrying about P of, for example, let me just show you this as an example. P of 4 squared, which is 16. I had to look at 1 minus P of 4 divided by n. And P of 4 had a special behavior. I figured that out because that's P of 2 squared. And so what I need to store is actually values up to the square root of the square root of the values that I'm interested in, which is nice, the fourth root. I don't have to store too much. Now, I just ran last night another version of this, and I went up to the square root of the square root up to 1 million. That's 10 to the 6th, which means n squared, therefore, is up to 10 to the 24th. And it works remarkably well. And let me just show you a graph of how well it worked. Here it is. This is from last night's run. What I'm showing you here in the x direction is the square root of n. And I've got 1,000. This is a logarithmic scale. So you see at the very far right, I'm up to 10 to the 12th. That's because I'm actually computing up to n being 10 to the 24th. And on the vertical scale, it's the computed error in comparison to the logarithmic integral interpolation of that table. I'm not actually computing the logarithmic integral, I'm interpolating it into some table, which is a lot faster than trying to compute it, I should imagine. And you see that at the beginning, it's a little bit low. The 1 on the vertical axis means exactly right. And it begins a little bit below that. And this is meant to be the error of the, my label isn't very good. I'm looking at pi of n here, not p of n. That is the cumulative number of primes less than some high number. And you see that the error goes up for a while. But once I get to the square root of n at about 100,000, it starts coming down. And it keeps coming down as far as I was willing to compute. This is about 4 hours of computation. And I assume that if I went further, it would keep going down. Every 10 years or so, I run this again because computers are more able, and I get a little bit farther. But this is kind of amazing that this probabilistic approach gets within, well, you can see the y-axis. I'm within 0.5% of what the logarithmic integral is. But there are a few caveats, and I must give you those caveats. And so I'm going to go back to the other one here. Caveats. Rounding errors. I'm doing this on a computer using floating point arithmetic. I'm using double precision floating point arithmetic, which is 64-bit floats, of which maybe 50 bits are actually of the significant bits. And so it's possible to get rounding errors. And the higher you go, the smaller is the value of P of n. And so P of n divided by n becomes a very small number. And then 1 minus that is very close to 1. It's very likely that I'm suffering from rounding errors up at this level. And how do you protect against that? I'll leave that question to the numerical analysts watching this. So going to a higher limit, giving it another 4 hours, is not certain to give us new insight. But the computers are a lot faster than they used to be. The other caveat is attempts to improve. So far have not worked. For example, you know that perfect squares are not prime, even though 4, I was giving some probability of its being prime, and 16. What if I know that it can't be prime because it's a perfect square, and I reduce by the necessary amount? It turns out this is a bad idea. It doesn't help. And I'm going to let, if he wishes, my brother David talk about his most recent idea of what you might do to improve this. So David, if you want to unmute and come on, feel free. Well, perhaps he doesn't want to. That's fine. But I must say, this is the whole idea was invented by my brother David back when I was in high school. I think he might still have been in high school too. He's a few years older than me. So David, you don't want to say anything about it? I have another family member here, Justin, who is David's son. So it's a real family event here. Well, if anyone wants to ask any questions about this or make any suggestions, I'd be glad to hear. Yeah, Hank.
Well, certainly, getting around the floating point issue is pretty easy. You can do that as either scaled integer arithmetic, or you can just use big num package or good old BC, right?
Yeah. Well, with BC, you specify the limit, and that's like a big num package. That'll make things a lot slower. But
That's
if
okay.
speed
Compute
is,
time's cheap.
that's right. It's maybe 10 times slower, but that's okay. I won't be able to go to a million, maybe only to 100,000 for the fourth root of n, but still I can compare it. So maybe that's a good idea. I should most likely do that, because this computation is easily enough described in the BC language. That's the binary calculator. Anyway,
Basic calculator. Yeah.
basic calculator, which I use very heavily. So maybe I don't think I want to use scaled integers. I would have to use big nums anyway. For those of you who aren't familiar with it, big nums are representations using multiple words of numbers that are too big to fit in one word, with software behind it that knows how to do such things as addition and subtraction and multiplication.
So let me just mention one other thing that comes to mind. So the reason that you're getting incorrect answers on this, to me, seems like it's basically a round off issue as well. But it's an integer round off on the basic model that you have. So have you thought about doing things where instead of thinking in terms of integers, you thought about instead of integers that were basically scaled fractions to begin with for computing whether it's prime or not?
Well, that's worth discussing offline. That's too complicated a question to answer immediately. But I think David's come in by phone. Are you there, David?
Yeah, I don't really have a microphone on this computer. So where we say probability, we should really be calling it pseudo probability, of course. But I'm going to, this is just like coincidentally, I'm going to do a refined version, which should be much more accurate. Okay, and that's going to use the fact that other than 2 and 3, prime numbers have to be of the form 6n plus 1 and 6n minus 1. Okay, and by using those as the sort of sieve, basically what this is a sort of a probabilistic or pseudo-probabilistic way of using the famous sieve of Eratosthenes. So by doing that, we'll get both larger intervals and much more accurate readings. So I'll write that up, and then I look forward to having Ray put that through the computer and see what comes out. The reason why just deleting squares, which are not prime, doesn't work is that it just distorts everything else. Okay, so I will write that up and send it to Ray, and then you can play around with it, depending on how much time you want to put in the computer.
Well, computer time is free until you run out of it. I don't know. It's only electrons. Many electrons get seriously inconvenienced, but other than that, it's fine. Well, I recommend this idea of presenting to the Keeping Current things you've played with in the past that caught your attention at some point and that you want to return to just to talk about them. So I do have another one that I do want to talk about later this semester. I'm going to tell you about my favorite base, which is base -5, but that's for another time. And you can ponder that meanwhile. And I hope to see you all next week at the Keeping Current seminar. But for now, let me just say goodbye. If you have any questions, email to me and I'll be glad to refer them to my brother. Bye now.